Bioinformatics Micromodules, the Viterbi algorithm. In this module, we introduce the Viterbi algorithm for finding the most likely state sequence. We will also briefly describe the Baum-Welch algorithm for learning the parameters of a hidden Markov model. The problem that we want to study this time is finding the state sequence with the highest probability given the observation sequence and the parameters of a hidden Markov model. This is usually the main use of the hidden Markov model because we are interested in inferring the hidden states based on the observations. Since we do not have a way to directly compute probability of Q given O and theta, we use the rule of conditional probability to turn it into the joint probability of Q and O given theta divided by the probability of O given theta. Since this denominator is independent of Q, for our purpose of maximizing the term across all possible Q, we only need to maximize the numerator. In theory, we only need to find out the state sequence Q that maximizes this joint probability term without actually computing the value of this probability. However, for the algorithm that we are going to discuss, we actually first compute the probability, on the way of which we collect information for inferring the Q that has this probability afterward. The algorithm that we are going to discuss is the Viterbi algorithm, named after the American engineer Andrew Viterbi. As you may have expected, it is a dynamic programming algorithm. As usual, we first need to define the subproblems and decide how the results are stored. As in the case of the forward algorithm, we define a table called delta this time with a step dimension and a state dimension, where each entry in the table corresponds to a subproblem. The entry delta Ti is a subproblem that has the same form of the original problem, but restricted to the first T steps and having the state in step T fixed to state I. The intuitions of this definition are similar to those of the forward algorithm, that we consider only the first T steps instead of all the steps to make the problem easier, and to fix the state of one step instead of all the first T steps to avoid the exponential number of combinations that we need to consider at the same time. With the dynamic programming table defined, as usual, we next introduce the initialization formula, the recursive formula, and the formula for getting the maximum joint probability from the table. Do not forget that in addition to these three standard formulas, we also need a way to get back the state sequence Q that leads to the maximum probability, which we will describe later. To initialize the table, we compute the entries for T equals 1. Based on the definition, delta 1i is equal to the joint probability of the first state being Si and the first observation given the model parameters. It is simply the product of multiplying the initial probability of state I by the probability of emitting the first observation by state I. Next, we have this recursive formula that computes an entry in step T based on the entries in step T-1. A formal proof of this formula will be shown later, as usual. Please notice that, unlike in the forward algorithm and the backward algorithm, where each entry is computed as a sum of terms that involve the entries in the previous step, here, each entry is computed as the maximum of terms that involve the entries in the previous step. Finally, after filling in the whole table, we see that each entry in row M has chosen one possible state for step M and considered all possible state combinations for the other steps. Therefore, the largest among them is directly the answer to our original problem. A formal proof of the recursive formula is shown here for those of you who are interested. You are again encouraged to do the derivation by yourself, and it will require only the three basic probability rules that we introduced in the previous module. Now, after filling in the whole dynamic programming table, to get the state sequence that leads to the maximum value of probability of O and Q given theta, we do a traceback of the table by finding out from which entry in the previous step that we obtain the value of the current entry. This idea of traceback is the same as the one used in the Needleman-Wunsch algorithm for finding the optimal global alignment after finding out the optimal alignment score. Specifically, every time when we use the recursive formula to compute the value of an entry, we record the one or more entries in the previous row that produce this value, indicated here by the red arrows. Then finally, after we have completed the whole table and found out the entry or entries in the last row that has the largest value, we determine the corresponding state sequence or sequences by following the red arrows backward until reaching row 1. Let's see an example of the use of the Viterbi algorithm. Here we have a fully specified hidden Markov model, and our goal is to find out the most probable state sequence given the observations tail, head, tail. To provide an easy reference, we have all the formulas related to the algorithm copied here. The completed table is this one. The entries in row 1 are first filled in using the initialization formula. Then using these entries, the entries in row 2 are computed. Let's look at the entry for state S1 together. Its final value is the maximum of two values, namely 0.1125 and 0.15. Since 0.15 is larger than 0.1125, we underline this value and record that this value is produced by the entry for state S2 in row 1, which explains the red arrow that points from that entry to this one. Then similarly, the entries in row 3 can be computed and the red arrows are added. Finally, from row 3, we find that the maximum value of probability of Q and O given theta is 0.0675. It is produced by the entry for state S1 in row 2, which was in turn produced by the entry for state S2 in row 1. Therefore, based on this traceback, there is only one state sequence that can give the maximum probability, and it is S2, S1, S1, or in terms of the names of the states, BAA. We now briefly discuss the third problem we originally defined, which is to learn the parameters of a hidden Markov model based on some examples. Mathematically, we want to find the values of the model parameters theta, such that the likelihood of the observation sequences is maximized. Remember that here O superscript D means that the training data can involve multiple observation sequences instead of one. In general, it is not easy to find the parameter values that maximize the data likelihood, and so the problem is commonly solved using a heuristic method, which runs fast practically but cannot guarantee that the result is always optimal. The algorithm that we want to discuss is the Baum-Welch algorithm, invented by Leonard Baum and Lloyd Welch. It is an expectation maximization algorithm, which iteratively updates the value of the parameters. Briefly, at the beginning, the initial probabilities, transition probabilities, and emission probabilities are all assigned some starting values, such as values randomly drawn. The values of these parameters are then updated based on the expectation maximization procedure, which would end up finding parameter values that give a locally maximized data likelihood. We will not discuss all the details of the algorithm, but only one interesting point. During the iterative update of the parameters, one quantity required is the one shown here, which is the probability that in a sequence, the state in step t is Si and the state in step t plus 1 is Sj, given the observation sequence and the current estimates of the parameter values. It can be expressed as a joint probability divided by the likelihood of the observations, as shown on the right. As explained in the previous module, the denominator is actually the first problem we studied, which can be solved by either the forward algorithm or the backward algorithm. What about the numerator? To simplify our discussion, suppose we only have one observation sequence. The numerator can then be re-expressed as a product of four terms, as shown here, which we will not formally prove. If you look at these four terms carefully, the first and second terms are exactly the entries in the alpha and beta tables, respectively from the forward algorithm and the backward algorithm. The third and fourth terms are model parameters, namely an emission probability and a transition probability, the current estimates of which in the iterative procedure can be used. The key message we want to deliver here is that in order to compute the probability of the state of a certain step, we can make use of both information from the previous steps and information from the latter steps at the same time.